The next example that we'll do together. Block M1 and M2 are stacked as shown with M2 on top. M2 is connected by a string to the wall, and M1 is pulled to the right with a force F big enough to get M1 to move. The coefficient of kinetic friction has value mu k along all surfaces. So the coefficient of kinetic friction here is mu k, here it's mu k. We need to draw a free body diagram, determine the tension, and find the acceleration of mass 1. I'd like you to pause the video at this point and try this yourself. Once you've done that, we'll go ahead I'll go ahead and share my free body diagram and calculations with you. Okay, let's copy this diagram here. And then draw a free body diagram for each. Undo. Alright. Now let's draw a free body diagram for each mass. Okay, starting with M2, I'll go ahead and circle the mass and identify all the contact points. I have a contact point here, which provides us with some tension. I have a contact point here, which provides us with a few forces. So there's a normal force of block 1 on 2. There is a force of kinetic friction that is pulling to the right. So that is force of friction kinetic 1 on 2. And then there is a force of gravity on block 2. And that covers all the forces that are acting on block 2. Then I'm going to go ahead and circle block 1. I have contact here and here, and I have a force being applied here. So we have a force F to the right. From this contact, we have a Newton's third law pair with kinetic friction 1 on 2. Basically, in the opposite direction, I have Fk 2 on 1. Then I also have a Newton's third law pair for the for the normal force. If block 1 pushes on 2 upward, then 2 pushes on 1 downward with the same magnitude and force. So we have N1 on 2 pointing downward. Then I also have the normal force from the floor, so N floor on 1 pointing upward. We also have force of gravity on block 1 acting downward, and then we haven't considered the force of friction between the floor and the block. So if the block is being moved to the right, that friction from the floor is also opposing your motion. So we have force of basically kinetic friction with floor on floor on M1 pretty much. So sorry, these subscripts are getting kind of involved, but I want to make sure that you're able to identify exactly the source of each of these forces. So I'll leave this free body diagram here for you to check. And what I want you to do at this point is pause the video and identify what the Newton's third law pairs are. And once you've done that, so N1 on 2 is a Newton's third law pair with N1 on 2. Those are mislabeled. So 1 on 2 is for the first block. On this block, it really should be labeled as normal force 2 on 1. And these two are Newton's third law pair. Then the kinetic friction 1 on 2 is the third law pair with 2 on 1. The normal force we already accounted for. Now, technically, the normal force from the floor and the friction force from the floor, if I were to draw a free body diagram for the floor, we would see the Newton's third law pairs for these, but we're not including that object in our free body diagram. So we don't need to be concerned with drawing those forces. Okay, so given these forces, now we can start doing some of the forces to first solve for part B, which is determine the tension in the rope. So to determine the net tension, it makes sense to let's go to the free body diagram of M2 and see what we can get. So some of the forces on M2 in the x direction is equal to force of kinetic friction 1 on 2 minus tension, and there's no acceleration because block 2 is being held by the rope, so that's equal to 0. Now to plug in the expression for kinetic friction, which is mu sub k times the normal force, I actually need to find what this normal force is. So let me quickly do the sum of the forces in the y direction for M2. So sum of the forces M2 in the y direction is N12 minus Fg2. Again, no acceleration in the y direction either, so N12 is just Fg2, and Fg2 is M2 times gravity. So when we plug things here in the x direction, basically we get mu sub k times the normal force 1 on 2 is equal to tension, and when we plug things in, we know that N12 is just M2G is equal to the tension force. So note what I've done is I've plugged in N12 from here into here. All right, and that gives us what our net tension forces in this problem. Once we have that, we'll go ahead and solve for part B. And part B is asking us to find the acceleration of block of mass m. So to find the acceleration of this block, let's go take a look at the sum of the forces for block 2. So starting with, so I'm gonna just draw a line here to organize my work. So sum of the forces on block number 1 in the x direction is equal to, well, I have F pointing to the right. Then I have F kinetic friction 2 on 1, F kinetic friction floor on M1. So minus Fk, I'm going to call them now shorthand 2, 1, minus Fk floor, FL, and then on M1, FL1. And those are all the forces in the x direction. And now this is going to not equal 0 because they told us that we pull hard enough for M1 to move, and they want us to find the acceleration. So the acceleration is going to equal some M1 times acceleration of mass 1 in the x direction. Now, reminder again, force of kinetic friction will be mu k times normal force 2 on 1, and the floor kinetic friction will be mu k times normal force from the floor on block 1. So we need to find these normal forces first. Okay, great. We know for a fact, since N12 and N21 are on Newton's third law pair, we know N21 is equal to N12, which is equal to M2G. So we can use that relationship. So basically, due to Newton's third law, what we know is that N21 is equal to N12, which is equal to M2G. Then, using the sum of the forces in the y direction, we can find the other normal force also. So sum of the forces in the y direction is normal force from the floor on 1 minus normal force of 2 on 1 minus force of gravity on 1. And those are all the forces in the y direction. So as we solve for the normal force, N floor on 1 is equal to, all of this, by the way, is equal to 0 because the block number 2 doesn't accelerate up and down in the y direction. It's just accelerating to the right. So all that being equal to 0, we can solve for normal force on the floor. It's just N21 plus Fg1. Plugging things in, we know from earlier that N12 is equal to N21 is equal to M2G, which I also wrote here. So this is equal to M2 times G, and then Fg1 is just M1G, and that's the normal force from the floor on block 1. So M2 plus M1 all times G. Now let's make some space for doing the sum of the forces in the x direction now that we have all of this information. scooch this to the right a tad. Great. So F is something that is given to us. Force of kinetic friction 2 on 1 is minus mu sub k normal force 2 on 1. Force of kinetic friction from the floor is mu sub k normal force from the floor on 1 equals m1a sub x. Alright, let's plug in the normal forces. We know n21, n21. And we know n floor 1 and n floor 1. Plugging that in, we get F minus mu sub k times m2g minus mu sub k times m2 plus m1g is equal to m1a. So all of that is equal to m1a. Okay, and we can keep it as ax. So now let's isolate ax and see that we can combine some like terms. So mu k m2g combines with mu k m2g. So doing some algebra, we basically get that F minus 2 times mu k m2g minus mu k m1g is equal to, all of that divided by m1 is equal to a sub x, which is the acceleration of block 1. So the acceleration of block 1 is given by how hard you pull, which is the harder you pull, the more it accelerates. And it's given by how much we're having to counteract the two terms in friction from having the two blocks here. So both of these providing some slowing down of the acceleration due to friction. Alrighty, make sure you go through this problem on your own and check your work with what's shown here. And let me just double check that all my algebra here makes sense. Yes, M1 and 2. Oh, also the question provides the masses in capital M, and I've used lowercase m. Apologies. Please try to stay consistent with whatever variables are given. So this little m and this little m should be capital M's really, and this one. All right.